So good afternoon, everyone. Welcome to the second webinar of the QueRa World Tour. Today, focused on the activities of QueRa with the partners in the UK. My name is Tommaso Macri. I'm the Executive Account Manager at QueRa, and I'm happy to introduce our guest today, Professor Jonathan Hirst from the University of Nottingham, Professor Ashley Montanaro who is the CEO of Phasecraft and professor at the University of Bristol, and Dr. Luigi Martiradonna, who is the head of business development at Riverlane. The agenda for today's presentation will basically cover some general concepts of neutral atom quantum computing from the perspective of QueRa. I will then pass the word to our partners, Jonathan from the University of Nottingham first, then Ashley from Phasecraft, and finally Luigi from Riverlane. I will then, the word will go back then to me with some discussions about the opportunities for collaboration and a brief conclusion. So QueRa is a quantum computing company based in Boston, Massachusetts. We employ about 50 between scientists and engineers. We also recently opened offices in UK and Japan. The goal of QueRa is to basically develop and commercialize quantum computers based on a specific type of technology called neutral atoms that are sufficiently scalable, meaning with a large number of qubits, and that are sufficiently resistant to noise. We already work with dozens of organizations and hundreds of users that execute jobs on our quantum computer, which is the one that you see here on the right on the tower of NASDAQ during an announcement that we made back in December of 2023. And for those who are listening to us today and are interested in potential opportunities to work at QueRa, feel free to reach out to us and have a look at the webpage QueRa.com/careers. Let me walk you through the main technological challenges of quantum computing with neutral atoms. First of all, neutral atoms are a very promising approach to perform quantum computing. They are all identical qubits in the sense that differently from artificial qubits such as superconducting qubits, they all respond in the same way to external electromagnetic fields, and so they do not need to be individually characterized. Secondly, today we have machines with hundreds of qubits, but there are already demonstrations with thousands of qubits in several academic labs, and these systems can scale to tens of thousands of qubits without requiring interconnects. This technology is relatively efficient, meaning that there are tools such as the so-called qubit shuttling that leads to an efficient problem encoding and also the exploration of early approaches toward quantum error correction. Finally, the machines that we build operate at room temperature, basically without the need of any cryogenic cooling device. And these basically facilitate the access of experimentalists to the machine and also reduce their footprints. The first quantum computer that we commercialize, that is currently available to the customers, both through the platform AWS Bracket as well as to an access model called Premium Access to work directly with QueRa, is called Aquila. It completed 2 years on November 1st of 2024, and this is the first and still the world's only publicly accessible quantum computer based on neutral atoms. Over the past 2 years, we increased the availability of this machine from about 10 hours to more than 100 hours per week, basically allowing users all across the globe to access almost in real time our quantum computer. With this device, we can explore problems across a wide spectrum of use cases, spanning from machine learning applications, both for classification and as well as for prediction. And this is something that we also developed internally through with our algorithms and applications team, putting together an algorithm called quantum reservoir computing that exploits the unique features of our neutral atom devices. The second class of problems goes under the name of combinatorial optimization. And this allows the techniques that we have at our disposal can cover problems such as the maximum independent set problem, which is a problem that can be natively mapped into our hardware, but also non-native optimization problems such as the Kubo problem that finds interesting commercially relevant applications. The third category of problems is called the quantum simulation, and it builds upon the original idea by the Nobel Prize-winning physicist Richard Feynman more than 40 years ago to simulate complex quantum mechanical systems with other tunable and controllable quantum mechanical devices, such as our neutral atom arrays, to simulate problems that can range from the equilibrium to the non-equilibrium phases of matters to more fundamental problems in science, such as the study of lattice gauge theories. The next generation, the second generation of machines is applied, basically exploit a different modality, complementary modality of quantum computation, which is called the digital or gate-based approaches. One of the main issues of today's quantum computers is the appearance of so-called noise that induces high error rates on our physical qubits, namely our neutral atoms, basically creating a very big obstacle toward the reaching practical usefulness for these machines. One way to overcome these issues is to apply ideas coming from an area at the interface of physics and mathematics, which is called quantum error correction. And the center of quantum error correction are the so-called logical qubits, which means ensembles or sets of physical qubits that can improve the error rate when we apply logical operations on them to useful levels. These reduced error rates allows therefore for longer and more meaningful and practical quantum algorithms. The second generation of machines that we built is called Gemini, and it is a quantum computer based on the digital or gate-based approach with hundreds of qubits today, but easily scalable to thousands of qubits very soon. It is a so-called ideal complement to classical supercomputing systems such as GPUs. It is easy to install and does not require any cryogenic cooling. From the perspective of energy consumption, it is also very efficient since it consumes less than 10 kilowatts of power. And it is a very interesting device to start exploring applications of logical or gate-based approaches in co-development modalities together with our quantum scientists at QuEra. Before giving the word to our partners, let me also highlight some recent commercial achievements, namely the strategic investment from Google in QuEra, but also the important contracts that we signed together with the UKRI to install a testbed machine in the UK, as well as the opportunity to install a digital quantum computer in Japan, located at IST, which is equivalent of the National Institute of Standards based in Tokyo, as a useful complement to a powerful quantum classical supercomputing system powered by NVIDIA's GPUs. So with this, let me give the word to our first partner, Jonathan from the University of Nottingham. Jonathan, feel free to upload your slides. I hope that you can do it without any technical problems. Yes, here we are.
Great. Thanks, Tommaso. Hopefully you can see the slide clearly.
Yes, I think they're still, yeah, we can see them, not in full screen yet, but feel free to start whenever you're ready, Jonathan.
Is that better?
Yes, that works great.
Great. Well, delighted to have the opportunity to contribute to the webinars today and to tell you a little bit broadly about the University of Nottingham, and then more specifically about our collaborative project with Phasecraft and QuEra, led by myself, my colleague Katie Insani, Ashley, who's on the call, and Tommaso also. So globally, maybe Nottingham's most famous for Robin Hood. There's a statue here in the city centre outside the castle. More sort of scientifically, perhaps the most famous person out of Nottingham is Sir Jesse Boots, who founded the Boots pharmaceutical chain, which is present, I think, in many countries and headquartered in Nottingham. And that's a bust of Sir Jesse outside the main university administration building. He donated the 300 and so acres that currently comprise the University Park campus, where the University of Nottingham is situated. Scientifically, perhaps most famous discovery in Nottingham was the invention of magnetic resonance imaging, and that's research and development activity that continues very much at the forefront of world-leading research today, alongside sort of related technologies and quantum technologies, brain imaging, a device there shown top left, allowing some of the best resolution brain imaging in children worldwide. And given maybe the historic links with Jesse Boot, it won't be a surprise that pharmacy and chemistry feature strongly in research activities in the university. And one relatively recent development has been the GlaxoSmithKline carbon neutral laboratory focused on sustainable chemistry. So this is where live drug discovery, synthetic medicinal chemistry is being done in a building where the aim is to be carbon neutral over a 25-year lifetime. So lots of features in the building, including those distinctive chimneys, reducing the amount of electricity required for ventilation, photovoltaics, and a host of other features that I won't dwell on in this short presentation. Computational and theoretical chemistry is a key activity within the School of Chemistry. There are 6 colleagues working across a range of method development: electronic structure theory, quantum chemistry, density functional theory, molecular simulation, analytical theory, and applying these to a raft of different application areas. And my particular interests lie largely under the column labeled biomolecular interactions. So 3 main strands of activity in my group. We sort of work our way up from the bottom, maybe conventional computational chemistry approaches applied to drug discovery. So this includes molecular dynamic simulations, free energy perturbation, quantum chemistry, and the so-called hybrid QMMM approaches, looking at various targets in collaboration with various colleagues, both within the university and further afield. So all those methods are very much physics based. We also have a large project looking at machine learning and its application to sustainable chemistry, funded by the Royal Academy of Engineering. And then what I'll spend a couple of slides on, one of our recent projects is in collaboration with Phasecraft and QuEra, looking at quantum computing algorithm development and its application to a problem in human health. So this is funded by Wellcome Leap with the specific remit of demonstrating an impact on human health using quantum computing algorithms. So the collaborative team is listed out here. Several computational chemists at Nottingham, some synthetic medicinal chemists, and also colleagues in the Queen's Medical Centre, in our Faculty of Medicine and Health Sciences, and then complementary teams at Phasecraft. I'm sure Ashley will be telling you a little bit more about some of the work at Phasecraft, and at QuEra we've already heard some of the activity there from Tommaso. So we've been in this project funded by Wellcome Leap looking at a covalent inhibitor drug discovery problem. And covalent inhibitors, while they do have a long-standing history, are really a paradigm that's grown quite considerably over the last decade. So there've been 15 plus approvals in recent years, and some very famous examples there covering a lot of different disease areas. And I guess the most historical example being aspirin, that everyone will have heard of. That we are looking specifically at myotonic dystrophy, and our collaborator and co-investigator David Brooke in the Queen's Medical Centre is a geneticist who discovered the gene associated with myotonic dystrophy. It's the most prevalent form of adult muscular dystrophy, and it's a disease that I guess is familiar to many and has no actual treatment. So one can mitigate symptoms, but there's no treatment leading to a cure. So our project focuses on the development of a hybrid quantum classical algorithm, and the idea is to enhance conventional density functional theory through the use of quantum computation, and then plug that into the hybrid QMMM approach, which is familiar to many in the pharmaceutical sector, and to use these QMMM calculations with the enhanced density functional to model the formation of the covalent bond between the protein. So that's the RS moiety shown on the left of the middle panel, forming a covalent bond with the inhibitor molecule on the right, and the motion of the electrons is indicated by the blue arrows. And the disease that we're focused on, and for which we have several hundred compounds with promising activity, is myotonic dystrophy. So we're sort of in the regime of lead optimization at the moment. So this slide here shows you some of the more sort of atomistic detail. So the structure of the protein target, CDK12, shown there. And our collaborators at Oxford have solved a number of new structures of the protein ligand complex, and then a zoom in on the active site. And if I click on this, we can see hopefully the actual molecular simulation. So the atomic level model of the motions of all the atoms. And this really allows us to drill into precisely which interactions are conferring the binding affinity. And these interactions change slightly as we go through the equilibrium simulation, and the challenge is really to model these quite subtle interactions with a suitably accurate level of theory. And well, there we go again. We can see then the size of the electronic structure problem. So the ligand on its own is 180 odd electrons, but we see here quite a subtle so-called CH pi interaction with one of the amino acids, one of the aromatic amino acids in the binding pocket. And if we wanted to include that tryptophan residue, then you can see the electron counts over 250. So we're working on an approach where one can use a NISQ device without having to sort of recompute or repeat all the quantum computation through this vehicle of an enhanced density functional that we can use in a well-established conventional QMM type approach. So it's very much a live project. We've just moved into the second phase, and we're pleased to be in receipt earlier this month of a conventional GPU server with 8 NVIDIA H200 GPUs and over a terabyte of GPU memory, and we're working on emulation of the quantum algorithms that are being developed, which will run on this server as a prequel to moving on to the QuEra hardware in the next, well, certainly within the next year or so. So very exciting prospects at hand. And let me stop there. Thank you very much.
Thank you so much, Jonathan, for the presentation. Ashley, would you like to start sharing your slides? And maybe while Ashley uploads his presentation, let me ask you very briefly, Jonathan, from an academic perspective, what role do you see universities playing in developing the next generation of quantum scientists and also potential engineers? How can we better equip students to contribute to the quantum workforce?
Yeah, well, I think universities have an absolutely pivotal role here. I mean, it's clearly, I think, a scientifically and technologically challenging area. It's clearly building on the foundations of mathematics, physics, and chemistry, so strong undergraduate programs in all those core areas are important, but then sort of master's level and PhD projects that bring together some of the different disciplinary strands are going to be critical here. So, I mean, it's very much a knowledge-rich domain that needs the university level education, both undergraduate and postgraduate, to feed into the skills needed in this exciting new area.
And you think the UK is well positioned for this type of revolution?
Absolutely. I mean, the UK university sector, I think, is very well regarded globally. The undergraduate programs start at quite a high level already, and I think UK government has been investing very significantly over the last couple of decades into quantum technologies broadly, and that's driven a lot of the provision of the higher level courses at postgraduate level in the UK.
Excellent. Thank you, Jonathan. Ashley, the floor is yours.
Great. Thanks very much, Tommaso, and thank you indeed for the invitation to speak today. So I'm Ashley Montanaro, and I'm co-founder and CEO of Phasecraft, the quantum algorithms company. And what I'd like to do over the next few minutes is to tell you a little bit about what we're doing at Phasecraft, and also a very little bit about our role on the collaborative project with Nottingham and QuEra, which has already been mentioned by Tommaso and Jonathan. And then finally, I guess, mention a little bit about the broader scene within the UK academic community working on quantum computing. So Okay, so I think it's pretty well accepted within the field of quantum computing and elsewhere that there are a number of really exciting applications of quantum computers out there, applications which are really important for practical reasons and which are beyond the capabilities of the world's best classical supercomputers. But in order to get to these applications, the performance of the hardware has to match the requirements of the algorithms and the software that are run on that hardware. If you want to do something useful with a quantum computer, the number of operations that you need to run the algorithm must be less than the capacity of the hardware, like the number of operations that hardware can execute. And at the moment, this is not the case. So if we want to solve certain very practically important problems on a quantum computer, the complexity of the algorithms outstrips the capacity of the hardware. And there are two ways of bridging this gap. Either the capabilities of the hardware have to improve, which is what organizations such as QuEra are working on. They're developing better and better performance quantum hardware that can execute more and more operations and has more and more qubits. But another way of bridging this gap is by developing more efficient quantum algorithms. And that's why what we're working on at Phasecraft. We're developing quantum algorithms which solve practically important problems within the capabilities of today's quantum hardware, or perhaps the quantum hardware we'll have in the next few years, as opposed to solely the quantum hardware that we're going to have in the next 10 years, 20 years, 30 years from now. This sort of hardware will be incredibly powerful, incredibly interesting as well, but it's our belief that we can do something interesting with quantum computers far sooner than that. So what sort of things are we working on as a company? So really our key goal is to get to this milestone of quantum advantage. So doing something with a quantum computer that outperforms what you can do with a standard classical computer. And we think that there are two really interesting and very promising directions in which to achieve this. One of these is modeling and simulating quantum systems. So what I mean by this is understanding the properties of some physical system where quantum mechanics plays a key role. So this is understanding that physical system at a so-called atomistic level, at a very sort of fine-grained level. And it turns out that if you want to do things like model the performance of a better battery or a more efficient solar cell, or as we've just heard, a new drug for some condition, then if you want to do this very accurately, in general, you need to understand the quantum mechanics within that physical system. And this is incredibly challenging for the world's best classical methods, because in order to do this classically, you either need to pay an exponential cost if you want to model this system very accurately, or you need to pay a very significant penalty in terms of accuracy if you want to do this efficiently on today's computers. So quantum computers can model these sorts of quantum systems natively without paying this exponential cost or this reduction in accuracy. But in order to make this promise make this promise real, one needs to think very hard about how to make the algorithms as efficient as possible. So this is one area that we're working on very hard, is developing efficient algorithms for simulating quantum systems in areas such as materials, molecules, and perhaps biochemistry as well. And we're also working on an area where quantum computing could play an important role, where quantum mechanics is not involved at all, at least apparently, which is solving hard optimization problems. So again, we've heard a little bit about this from Tommaso already. This corresponds to solving problems where the intent is to optimize over exponentially many possible solutions, and where this may be very challenging to do using classical computers. This might correspond to problems like finding the most efficient energy network. This is something that we're working on together with National Grid. It might be a problem such as finding an optimal portfolio of stocks in financial services, or it might be something involving optimizing a logistical network for shipping physical quantities or perhaps data around. And in all of these cases, there are problems which are extremely challenging to solve, where you in order to solve them classically, people resort to heuristics or sort of approximate solutions, and where it's possible that quantum computing could enhance these heuristics. And in both of these cases, quantum computing could make an impact even in the near term. But in order to do that, we need to think quite hard about the algorithms and not just use the textbook ones off the shelf. And I want to say a little bit now about how we're doing this, in particular in the context of materials and chemicals modeling. So the way that we think about materials modeling in general is as follows. So first, using our understanding of the physics and chemistry of a particular system we want to model, which might be, for example, a new battery cathode material, we restrict the problem down to the key part of it, so the most important and sort of a small part of it, which captures the essential physics and chemistry without needing to address the whole thing on the quantum computer. We then come up with ways of encoding this problem efficiently on the quantum computer. That's effectively representing the electrons within the quantum system in terms of qubits. And we have some very efficient ways of doing this via what's called fermionic encodings. And we then develop efficient quantum algorithms to solve the problem. And the sorts of problems we're thinking about here are things like producing low energy states of that quantum system and calculating their properties, or maybe modeling the time dynamics of this physical system. And putting all of these different ingredients together is what enables you to get significant reductions in the cost of that materials modeling task. So these different ingredients, such as reducing the problem to its key aspects, representing it in the most efficient way, and optimizing the algorithm that you run, they combine together to produce an ultra efficient total algorithm design, which is encapsulated in a whole software toolchain. And putting together all these different ingredients gives significant reductions in cost compared with the best previous quantum algorithms that were developed. So if we look at a particular material such as strontium vanadate, for example, which has applications to developing next generation solar cells and batteries, this is actually a notoriously difficult material for classical methods to model. And the best quantum algorithms as of a few years ago also seem to be so you also seem to find it very challenging to model this material. But it turns out by putting these different ingredients together, you can get a reduction in cost of the order of 1 million times or more, depending on how you count it. And you can see the complexities of quantum algorithms for solving this and over 40 other different materials on our website, materials.phasecraft.io, which gives further details about our techniques and how they're applied to a number of different material systems. And this is actually still not quite enough to make modeling these different materials within the capabilities of today's quantum computers. So we actually built on this idea to develop something we're calling quantum enhanced DFT, density functional theory. And the idea here is that we build on this amazing existing workflow and pipeline that already exists classically, DFT, density functional theory, which is one of the most successful ways of modeling materials and chemical systems classically. The only thing that it struggles with effectively is the quantum correlations within the physical system that it's trying to model. And what we're now able to do is to use a quantum computer to just address that quantum correlation part and offload all of the rest of the modeling and simulation tasks to this existing classical workflow. And this means that we firstly reduce the requirements on the quantum computer, so we don't need to solve the entirety of the problem quantumly, we just need to solve a part of it. And we also are able to plug into this existing toolchain, which means that if we can just nudge it in the right direction, we have the hope of improving its results and giving us something which is higher quality than we could get just with that classical solution. And we've already seen some really interesting results for this for material systems, such as the notorious Fermi-Hubbard model in condensed matter physics. And as Jonathan mentioned, we're now building on this within this collaboration with Nottingham and QuEra, where we're looking at applying this technique and others within the framework of modeling covalent inhibitors within biochemistry. So this is a wonderful collaboration because we're able to combine the quantum algorithms designs that we're developing with the chemistry expertise from the University of Nottingham and the world-leading hardware that's coming from QuEra to achieve, we believe, some very nice results. Okay, and just before I finish, I want to mention briefly something about quantum computing on the academic side within the UK more generally, because I do have another hat, which is as Professor of Quantum Computation at University of Bristol. And the UK, as Jonathan mentioned, has a extremely strong and long-standing tradition in quantum computing theory, specifically, going back to the late 90s even, as well as a very strong tradition in quantum experiments. And I've just highlighted here a few of the groups in the UK working on quantum computing theory, although there are many others out there as well. So in Bristol, for example, where I'm from, we have experts such as Professor Noah Linden and Dr. Nicholas Breukman, who are working on things like verification of quantum computers and quantum error correcting codes. I won't list everybody in all of these other institutions around the UK, but what I'll say is that the spectrum of activities covered in all these different institutions includes things ranging from quantum algorithm design, connections to condensed matter physics, so connections to materials science, verification of quantum computers, quantum machine learning, connections to fundamental physics and high energy physics and quantum gravity, and connections to other aspects of computer science, other aspects of theoretical physics, other aspects of mathematics. In fact, I would say pretty much every area of quantum computing theory is represented within the UK academic effort. And I would also say as well that the UK has very strongly invested in quantum computing over the years, most recently in the shape of the £2.5 billion investments in the UK Quantum Technologies Programme in the next phase of that, which is a 10-year commitment taking us through to the middle of the next decade. So we at Phasecraft are thrilled to be part of this UK community working on these areas. And that is everything I wanted to say. So thanks again, Tommaso, for this opportunity.
And thank you so much, Ashley, for walking us through the recent developments at Phasecraft. Luigi, maybe you would like to start sharing your slides, and while we do so, maybe a quick question also for you, Ashley. So at the beginning, you mentioned that a Phasecraft is known for advancing, practical quantum algorithms, and especially the interplay between, pure algorithmic innovation and hardware development. How do you see your role in this specific, area of both research as well as, commercial potential products that could come out, could spin out of this effort, and most importantly, related to the technology that we are also developing at QuEra?
Yeah, so that's a really nice question. So we as a company see ourselves as really working hand in glove with the world's best quantum hardware developers to make the applications that users want to address on their hardware actually practical. And this involves really understanding the hardware in great detail, as well as understanding the applications that users want to run and all of the quantum algorithms and quantum information in between. So that's why we love working with companies like QuEra, because it enables us to really work with these world experts on the hardware, and also indeed run on the hardware itself. And in the context of neutral atoms specifically, I guess I would just say that the technology has really come on a lot in recent years, and it's been incredibly impressive to see how it's continued to develop, and some of the recent breakthrough results that have come out implemented using this technology. And for us, I think it's a really exciting platform of thinking of these sort of materials modeling type applications, and in particular these ones that have this sort of periodic structure, or involve sort of solid state systems where maybe one needs quite a large number of qubits, where they're sort of laid out in a sort of regular way, but where we have some flexibility in terms of how we implement interactions between them. And in some of these cases, we think neutral atoms are a really nice fit. So that's why we're very much enjoying this collaboration.
Thank you, Ashley. Thank you so much. Luigi, please.
Yes. Okay. Can you hear me?
Start. Yes.
Okay, wonderful. So, well, thank you very much, Tommaso, for having us in your QuEra World Tour. So I'm Luigi Martiradonna. I'm a head of business development at Riverlane. And indeed, Riverlane is a partner of QuEra in the UK. We are supporting them in the delivery of the quantum computing testbed that QuEra is preparing for the National Quantum Computing Center in Harwell, as Tommaso mentioned before. So let me tell you a bit more about Riverlane. Let me see. Okay, it's working. So we are a company, a quantum engineering company based in Cambridge. We have more than 90 employees with a very diverse background. So we have quantum physicists, we have hardware and software engineers, we have mathematicians, and all of them united basically by the mission of making quantum computing useful sooner. Which sounds very cool, but what does it mean in practice? So the way in which we want to achieve this goal is basically by focusing on what we consider the critical issue that quantum computers face today, that has been already mentioned in the previous talks, which is errors, basically. So if you consider a quantum computer today, not specifically only neutral atoms, but also trapped ions, also superconducting, etc. So you will see that basically they will be affected by let's say on average 1 error every 1,000 operations, something like this. Whereas, I mean, from the application side, well, I mean, you probably need to perform operations like millions or trillions of operations to get to useful results. And so there is clearly a gap here. And if you run this kind of operation on the computers today, you will be just overwhelmed by errors. So you will not be able to trust the results. So as Ashley explained before, I mean, one way to fill this gap is basically work on the algorithms and make sure that basically you reduce the resources needed by the algorithms to run this application, which is, I mean, a great work and effort that must be done by companies like Phasecraft and others, basically to making quantum computers useful sooner. Also, the way in which we are approaching the angle is from the bottom up, so from quantum error correction specifically. And as Tommaso mentioned, quantum error correction is basically a way to implement redundancy in a quantum computer. So if you have a single unit of information, basically, instead of encoding it into a single physical qubit, what you do is encoding into a logical qubit, which is an ensemble of physical qubits, basically. And if you do it in a clever way, what happens is that even if one of your physical qubits or a few of your physical qubits are affected by errors, you will still be able to retrieve the correct information from the logical qubits, so from the ensemble of physical qubits. And this will basically protect your information. You will get more reliable results. If you consider the full stack of a quantum computer, so with the qubits at the bottom and the application level at the top, Riverlane is focusing on what we call the QEC stack, which is this bit in the middle, basically the hardware and software components that basically talks to the qubits through the control system. So take the measurements and then transform them into reliable, error-free logical qubits that are then used by the applications. And there are, of course, various, if you're following basically the literature of quantum error correction, you may have seen that there have been amazing results in the past year. One of these is definitely the work that the QuEra performed with in this collaboration with the University of Harvard, in which they basically demonstrated up to 48 logical qubits on a single neutral atom platform. So I mean, it's one of the milestones basically of the field. The approach that we are taking at Riverlane is slightly different in the sense that we do not own any qubits, but we basically build the QEC stack that will be able to operate horizontally on the different type of qubit modalities and help basically the qubits of our partners to improve their quality, improve their reliability. So we have 100 people basically that is just focused on this part of the stack. So why do we want a full company just working here? Because actually it is a very hard engineering problem to solve quantum error correction at scale. And just to give you an example of what the quantum error correction stack needs to do continuously while the quantum computer performs basically its applications, this is a representation on the right of the quantum error correction cycle. And so we start basically from the qubits at the bottom, And then we measure a few of these qubits to extract basically a stream of error data, which contain information on whether an error occurred or not. And then you need to send this information to the decoder that needs to basically perform sophisticated inference algorithms that are able basically to precisely, accurately localize the errors in the qubit array. And then the important thing is that then you need to send the correction information back to the quantum processor very quickly in real time before the quantum processor starts doing the next round of operations, basically. Otherwise, the errors will keep accumulating and you will not be able to correct them anymore. So depending on the type of qubits, you may need to basically close this loop or perform this cycle even in less than 1 microsecond. And if you're thinking about basically a large-scale quantum computer like with millions of qubits, then of course this means that you will have to add streams of millions of data to be processed in a microsecond. So we're talking about terabytes, hundreds of terabytes of data per second to be processed continuously. So that's why it's an interesting engineering problem to solve. And the way in which we are solving it at Riverlane is by relying on hardware acceleration. So basically, we design very accurate and fast decoding algorithms, and then we port them on FPGAs and ASIC chips in order to get basically both the accuracy and the speed that are needed to perform quantum error correction at scale. We were very proud of the results that we published in 2023. This was the first demonstration of a QEC SIP chip, basically, so a decoder on an ASIC. And we got very good performance for this first attempt. So the chip was very accurate. We had the logical error rate of 10 to the minus 12. It was also very fast, so the cycle was completed in less than 1 microsecond, and also it was pretty energy efficient, so it only consumed basically 8 milliwatt to operate. Now we're working on the second generation of the QEC stack, what we call DeltaFlow 2. And as you can see, so this will be released basically in the next few weeks. You can see here a rendering of the system, and this is basically a rack mountable box. Inside you will find the hardware accelerated decoders that we're building, and this system can be basically plugged into the control system of a quantum computer in order to perform quantum error correction. So this solution will handle up to 250 physical qubits, but actually a metric that we are mostly more interested in is the number of error-free quantum operations, so the QOPs that this system will enable. And so this generation will enable up to 10,000 QOPs. So it is compatible with the error correction codes that are mostly historically widely studied in the past years. So the surface code and the repetition code. And what you will be able to demonstrate with this kind of technology will be basically that you can keep your logical information, your logical qubits alive forever, if you want, in the experiment that we call streaming quantum memory demonstrations, basically. We do not stop here, so we are already planning our work for the next few years, and by 2026, we are aiming at handling more than 1 million error-free logical operation. With the DeltaFlow Mega system that we will build by 2026. Interestingly, this will not only do memories, but also be able to perform logical operations. That means universal gates. So Clifford gates, non-Clifford gates, all together that will enable basically universal fault-tolerant quantum computing, and it will also be extended to the other types of error correction codes, including the QLDPC codes. I just wanted to take 1 more minute to discuss another type of technology that we are developing, another product that we are developing, which is a QEC Explorer. So this is actually a software tool. So it's not hardware-based, but a software tool that is cloud-based, and it gives access basically to the highly accurate decoders that Riverlane is building. So if you are not ready basically to perform real-time quantum error correction, but you want to have a basically test the what we call the QEC readiness of your quantum processor. So you want to have an idea of how logical operation, how a logical qubit would perform in terms of quality, basically on your QPU. So what you could do is basically run experiment, small scale experiment on your QPU, and then send the measurement to the cloud through QEC Explorer, which will be able basically to extract these QEC metrics that will be able to benchmark the performance of your processors. And so you can use it basically to, for example, test the effect of a calibration, a better calibration of your QPU, or maybe to identify the key noise sources on your chip, and then basically build the next upgrade of your processor that will perform better in terms of logical performance, etc. So basically, if you consider the complete solution here, so you can start basically with testing the performance of benchmarking, basically the performance of your processor using the offline calibration of QEC Explorer. And then when you're ready to move to the real-time experiments, then you can integrate the Dataflow QEC stack in your quantum processor and do quantum error correction at scale and at speed with high accuracy. So yes, that's all I wanted to say. Thank you very much, and I'm happy to take questions now or later. I'll let Tommaso.
Thank you. Thank you, Luigi. I think we actually have a question from the audience regarding your Dataflow solution. And the question was whether Riverlane's Dataflow solution scale for network QPUs for network level QEC.
So what we are doing is at the moment, basically the solution that will be released in the next few weeks. As I said, I mean, his build is working on specific sides of the systems, but definitely the handling of a larger and more complex decoding the solution is definitely something that we are looking into. So the architecture that basically we are designing will be able basically to let multiple decoders talk with each other, be synchronized all together, and so basically we'll be able to handle multiple decoding tasks that will either be covering different types of decoding processes together, or basically handle different zones of the same QPU, or also networks of QPU connected together. So that's the idea. Basically, the architecture that we are designing, it should be able basically to also handle this type of expansions, basically to scale up.
Thank you, Luigi. Thank you so much. So we're heading towards the end. Let me briefly summarize the possible ways to collaborate with QuEra. Basically, by essentially acquiring one of our quantum computers for installations on-prem, relying on the support of QuEra's engineers and scientists, and also to help develop the local quantum computing community where the machine will be hosted. The second modality, of course, could be through the cloud access, either through our service, AWS Bracket, or through a direct interaction with our scientists through the so-called premium access model. And very recently, a couple of weeks ago, we also advertised our new co-development program to enable long-term collaborations with the strategic partners to co-develop what are called, technically speaking, killer app for quantum computing. Recently, we also created the so-called QuEra Quantum Alliance that by now counts more than 20 partners worldwide. The Quantum Alliance is thought to basically enable the outreach and the adoption of neutral atom quantum computers, essentially in close collaboration with many commercial partners. And of course, if you're interested to join us in this effort, feel free to reach out to us. This is my email address, tmacri@quera.com. Before concluding, let me, of course, acknowledge our speakers from today, Professor Jonathan Hirst from the University of Nottingham. Thank you, Jonathan. Professor Ashley Montanaro from Phasecraft, and Dr. Luigi Martiradonna from Riverlane. With this, I would like to conclude and thank you all for the attention. Thank you, and see you at the next webinar.
Thanks, Tommaso.